어, 이벤트, 여기까지. 너무 싸. 여기까지? 네, 다음 주 토요일까지 있어. 논문 잘 챙겨. 아니, 이거. 근데 초반이긴 해요, 뭐. 이거. 네. 아, 뭔가 자료 만들면서 뭐 했나 싶어가지고. 어제 너무 심파가. 아, 아. 아이고.
All right, let's go ahead with the schedule. Today we will see lecture by Rosalinde and Gian and discussion by Haesung, right? And also next week, two invited lecturer speakers. Thursday, he will be coming to a classroom, but the other Tuesday on 5th, the lecturer will not come. He will be on Zoom online. So we will have a whole Zoom class on Tuesday and 5th. And also we will have a trip to Criso on Friday, the other week. And here is the list I got from TA. We have 15 members altogether until now. So, and I'm working on how to get there through the transportation. Any other question? Any question? Schedule, other items?
C'est une nouvelle solution.
Sorry? Say again? No? Then we move on to the.
C'est ça.
Yeah.
Encore qu'une seule fois la liste du snake pose.
Sorry, do you have any question on
Donc
this?
ça, c'est pour remplacer ça. Et ça, après, c'est les positions. On est d'accord que ça, c'est même ça, et ça fait la même.
He's speaking without any intention, right? Right? Go ahead.
Where is here the presentation mode?
Control F. We have a section on the right-hand side. And it has a disable this.
Okay. Hello, my name is Rosalinde Baubeck, and I will present to you today about dynamics of ship motions. First of all, I will do a brief introduction on how can a ship move at all and why does a ship move, and then I will go into a more detailed explanation on how those different motions look like and what can cause them and what are the risks of those. And in the end, I will do a very brief introduction into mathematical modeling of ship motions. And then the second part of the lecture today will then be Zian to talk about how to stabilize a ship that does those motions. Okay, so why and how is a ship moving at all? Everything moves because there are forces that are acting on an object. And in the case of ships, it's mostly wave and wind forces, but also turning forces and propulsion forces and a lot of other kinds. Then the ship itself has certain parameters like its shape and its size and its weight. And all of those have an influence on the location of the center of gravity and also on the center of buoyancy, which we already learned earlier this week, that those two parameters are very important when it comes to how a ship is moving and how a ship is stabilized. So those factors influence how those forces make the ship react in a certain way. And then in the end, we have the movement. The ship in the end is also just a 3D object, and as every 3D object, it also has 6 degrees of freedom in which it can move. So 3 translational and 3 rotational. And of those, I want to talk a little bit more now. But first, we have to define a reference axis so we can do that. Now, for the origin point of the coordinate system that is mostly used, I saw some different literature. Some seem to use the center of gravity for the origin point. Some use like a very specific point within the structure. But then the axes were all defined in a similar way. As in the x-axis, the longitudinal axis goes through the length of the ship, parallel to the waterline, while the y-axis or the transpose axis, or sometimes also called lateral axis, goes perpendicular to that, also obviously parallel to the waterline. And it is also defined that the positive y-axis side is the port side and the negative y-axis side is the starboard side. And then the z-axis is obviously the vertical axis going up. Now we come to the motions. First, translational ship motions. Ship motion in x direction is called a surge. And it is mostly caused by wave or wind forces that are striking the ship from the fore or from the stern. And the reaction of the ship is then a rapid de- or acceleration in a longitudinal direction. And the risk of those motion is that it can cause a lot of stress on the hull. And it also can move cargo around if it's not secured properly. Then translational motions in the y direction is called a sway. And this happens if the wave is moving perpendicular to the motion of the ship. And then the vessel will start to shift between the port and starboard side. And this can also potentially create a rapid acceleration or deceleration effects. Then we have the motion in that direction, which is called the heave. And this happens when a wave strikes the ship along its path of motions. And it can create a force imbalance between buoyancy and weight. We already heard a lot about that in the last lecture. And this then creates an upward and downward motions of the ship. And again, similar to the surge, this can also create a lot of stress on the hull and also moving around cargo that is not supposed to move. Then we come to the rotational ship motions. First, the rotation around the x-axis is called rolling motion. We also already learned a lot about that in the last lecture. And it can be caused by waves moving perpendicular to the ship motions, by wind forces, by cargo shifting, by a hard over of the rudder. A lot of different things. And the result is then a side-to-side rolling of the ship, which in the worst case can lead to capsizing of the ship. It can also induce a lot of inertial forces on the ship structure. And in the case of a ship moving passengers around, it also has to be noted that this can lead to a lot of seasickness, which is not so nice for the passengers. Then rotation around the y-axis is called pitch. Again, this is mostly caused by wave forces. And it is rotation about the transverse axis, which then creates an up and down motion of the fore and the stern. And generally, it can be said that the bigger the ship, the smaller is in general the angle of pitch. And it can lead to seawater on deck. It can also lead to propeller racing. And again, it can put inertial forces on the ship structure. Then last of those, we have the z-axis, the rotation around the z-axis, which is called a jaw. And again, the most likely causes are wave forces. Sometimes it also happens during vessel towing. And the reaction is a spinning of the ship around its vertical axis. And since the ship then looks in a different direction, it can cause a course deviation, which you usually don't want because you want the ship to go in the direction you want the ship to go. Okay, those were the movement in the 6 degrees of freedom, but there are some other ship motions I want to talk about. One thing is hogging and sagging, and it happens if a wave moves along the length of the ship. And as we also learned last week, at the top of the wave, there's a higher buoyancy than at the bottom of the wave. So we have a different buoyancy along the ship's length, and this can lead to a curvature in the ship hull. So if we have like the waves high is in the middle of the ship and the wave is low at the bow and at the stern, we will have a hogging movement. And if it's the other way around, the waves are high at bow and stern and low in the middle of the ship, then we have a sagging motion. And the risk in that it can happen that the ship will start to oscillate between hogging and sagging quite fast, which can cause vibration. And this is can lead to a lot faster material fatigue. And lastly, we have also something that is called slamming, which again is induced by waves. And what happens is that every time the ship strikes the water surface of the wave, there's a sudden deceleration. Any side of the ship with heavy motion, but the most common form is the bow slamming, when like the front of the ship like clashes with the waves like again and again. And this can cause very, very high loads on the ship structure, and is something that has to be kept in mind when a ship is designed, because a ship has to be designed in a way that it can withstand those kind of loads, even though they are not the standard loads that would happen on a ship. Okay. Then I have a short summary of the effects different motions can have on the ship. First of all, motion always creates loads, and loads always have an impact on the structural integrity of the structure, then the material response, and lastly also on the stability, which is again what Zian will talk about later. It is also noted that in general rotational motions seem to have more, or are more important for stability questions when it comes to the ship, while translational motions have to be kept in mind more for the structural parts, since they induce large stresses on the hull. It is also said that we don't live in a perfect simulation where there's only ever one type of motion or one type of force acting on a ship. There will be always a mix of motions happening. And if multiple types of motions happen at the same time, this can lead to torsion, which again puts even more stress on the hull. And it's also noted that the longer the ship, the more likely or the more stronger those torsion forces can get. Okay, then I want to talk very briefly about the topic of mathematic modeling ship movement, because it is a very important topic, because to be able to properly operate a ship, we need to know how it is moving and how it will react to different conditions. And therefore, simulation is a very important topic. Now, there are a lot of different models out there which do different kinds or do different calculations on that range from kind of complicated to very complicated. And so I cannot go over all of them. And the one I want to talk about right now is the MMG model. MMG stands for Maneuvering Modeling Group, which is the group that introduced this model. And it was proposed in 1977 at the Japanese Towing Tank Conference. So it's not the newest model out there, but a lot of models are based on this model, which makes it still quite an important model. And there has been an effort to standardize the basics of this model. And the 4 elements of the MMG standard method are the maneuvering of the simulation model, the capture of hydrodynamic force characteristics, and the determination of hydrodynamic force coefficients, and the prediction model for maneuvering motions of the ship in full scale, which brings it all together. Now, going over the whole model is also a little bit much for this lecture. So I just want to talk very briefly about the core functions to explain the motions of the ship. And, these are the 3 equations that model how the maneuvering motions act on a ship in still water. And it's they show the surge motion, so in X direction, the sway motion in the Y direction, and the yaw, the movement around the Z axis. And as you can see, they take in within the equations they use the ship's mass, the freeload of the ship, and also the different masses induced in different directions. The velocity and acceleration, and this parts those vectors in the search direction, in the lateral direction. It takes into account the yaw weight and the yaw acceleration, and also the actual location of the center of gravity of the ship. And in case for the yaw weight, also the moments of inertia, the one around the center of gravity, and also the added moments of inertia. And it then equals those with the forces that are acting on the ship's hull and the forces that are induced by the propellant and also by the rudder, by the steering of the ship. Yes. So as I said, I won't, in this lecture, I won't go into more detail on this model, but for anyone who might be interested in this kind of topic, in the end of the presentation, I reference a paper which explains this model quite well. So if you are interested in that, you can read it up there. Then I am at the end of my presentation. Thank you for listening. And if you have any questions, I'm happy to answer them.
From my previous lecture. Small additional comments. One is about the equation of motion. This is very, very complicated. So let me show you. Video. See, you remember this one from your mechanics? So there is a spring mass damper system. Right? You remember this one? And equation comes like this one. So there is maybe another way. This is a inertia term depending on acceleration. This is a damping term depending on the speed, and this is a spring constant and spring and displacement, right? And then external forces there. So if you move this one in this way and this way, you can arrive at this equation. You see, there are very complicated, looks like a complicated one, but this one is acceleration term. This is a speed term. This is a displacement. And then external forces here. Same structure of mass damping equation. And it is for surge motion, it is for sway motion, this is for yaw motion. There are more because we have a 6 degrees of freedom. But anyway, this is inertia and mass term, and this is damping related term, and this is spring constant term. And then external that you can understand. In detail, it's very complicated equation because ship is big and complicated. Another one is about Bose-Fleming. I just can also show you a ship. Fleming damage and image like this one. When you see this, this is a bow part of the ship, and the bottom of the keel plate is damaged because of the ship is this is related to pitching motion. Wave is coming, so ship is moving this way. And pitching, when returning back to the water, it can hit to the water surface. That is a force limit. And depending on the acceleration and speed, it can be high enough to damage the. All right, that's good enough. And then we can move on to Jian. And we open this one. Right.
Okay, hello everyone. My name is Yen, and today I'll be going through the second part of the lecture today on dynamics of ship motion. So Rosalind just now has covered on ship motions and their equations. So for today, I'll be focusing on ship stability, focusing particularly on roll, pitch, and yaw stability. So there are 6 types of ship motions as covered by Rosalind just now: surge, roll, sway, pitch, yaw, and heave. We'll be focusing on rotational motions today: roll, pitch, yaw, and yaw motion. So let's take a look at roll stabilization. A ship's roll is caused by the generation of greater buoyancy when the wave causes the water level on one side of the ship to be higher, thus causing the ship to lean on the other side. So when you want to add a stabilizer to counter this roll stabilization, then you need to look at how the tipping force is acting on the ship, and you need to add a stabilizer which is in the opposite direction of the tipping force, and also the magnitude of the force matters. Yeah. So these are some examples of the types of roll stabilization methods: bilge keels, fin stabilizers, anti-rolling tanks, and rudder roll stabilization. And I will go into more detail about this. So first, bilge keels. They are a very simple design. They are approximately perpendicular protrusions to the bilges of the hull under the ship. And what they do is that when the ship is rolling and they move up and down, they will create turbulence, which will actually dampen the force created by the rolls created by the waves. Yeah, so this is just a simulation to illustrate how the force is created by the bilge keels. The second method is fin stabilizers. They are also underwater retractable or non-retractable wings at the bilges of the hull, and they can look similar to bilge keels, just that they the difference is that you can change the angle of the fin stabilizer. So if you take a look at the simulation here, when we change the angle of the fin stabilizers, the water flow actually changes according to the direction of where the fin stabilizer is facing, and this will create the energy change according to the direction that it is facing. Yeah. The next method is anti-rolling tank. It is a type of system that uses water to control the rolling motion of the ship. So I have a video here to show you how it works and to illustrate the motion.
Another method of stabilization is passive anti-roll tanks. These are tanks installed in the extremes of the ship's breadth. The key to these is in the design of the crossover pipes. Normally, with the ship upright, they're going to have the same amount of fluid on each side. As the ship leans over one way, the fluid in the low side is going to increase. If you can control the flow of fluid enough, you can have the maximum amount of weight.
Sorry. Yeah. Hold on. Give me a second. Okay, I will start again because it was very soft just
Another
now.
method of stabilisation is passive anti-roll tanks. These are tanks installed in the extremes of the ship's breadth. The key to these is in the design of the crossover pipes. Normally with the ship upright, they're going to have the same amount of fluid on each side. As the ship leans over one way, the fluid in the low side is going to increase. If you can control the flow of fluid enough, you can have the maximum amount of weight in that side as the wave moves across the ship. Theoretically, if you keep the fluid there while the wave crest is there, it can help to counter the roll. Of course, you need to release it to let it flow to the other side at just the right time so that it's ready to counter the next wave crest as that approaches. You can add in more control onto these tanks, making them semi-active. Or you can even add in a set of pumps, controlled by a gyroscopic stabilisation system that can pump water across whenever it's needed. This would be a fully active system, and these sort of stabilisers are good on ships. They would work okay on cruise ships, as they can actively counter the force of the roll as it's happening. Unfortunately,
So the last but not least type of roll stabilization is rudder roll stabilization. It makes use of the movement of the rudder to create a roll moment which will counter the roll moment created by the waves to dampen it further. So taking a look at these 4 types of roll stabilization and comparing their individual benefits and challenges. For bilge keels, they can be simple and inexpensive to install, but the disadvantage is that it increases hull resistance. For fin stabilizers, it can be highly effective in countering the roll motions of the ship, but it can only be effective at high speeds for ships, and it can be very expensive to implement. For anti-rolling tanks, it is very effective at all speeds, but the challenge is that it requires a large space and weight to implement. And lastly, for rudder roll stabilization, the benefit is that it requires a relatively small space, but it is very ineffective at low speeds, same as the fin stabilizer, and it requires a highly capable steering system to implement. So each of these stabilizations have their own benefits and challenges. So it depends on the type of ship, the size of ship, and also what speeds do they need in their course to consider what kind of stabilizer you need for that ship. But oftentimes, the stabilizer is already implemented for the type of ship. So they just have to choose the type of ship, and the stabilizer will be in the ship. So there are also other roll stabilization ideas, such as the spinning gyroscope, which was implemented first in the 19th century. And for the Bessemer saloon, it does not actually directly counter the roll motions of the ship, but what it does is that it creates a system that allows the passenger cabin to be installed on gimbals so that it can be placed horizontally when the ship is moving. So it actually allows the passengers to be prevented from suffering from the impact of the ship roll motions. Yeah. So it's a very interesting idea concept. So let's move on to pitch stabilization. Oh, I have a video here to show you about the slamming of the ship. Okay. So it's just to illustrate the slamming of the ship, like what Professor and Rosalind had mentioned just now. And there are pitch turns. Cause the water to forward like this. So to counter this pitch stabilization issue can be achieved by changing the speed or the course of the ship, or if you distribute the load appropriately on the ship, and you can also use horizontal fins to counter the motion. So one very good example of pitch stabilization is the use of hull vanes. It is located at the aft of the ship, and I have a video here to explain the use of the hull vane.
Fourth effect manifests itself in waves. So as soon as the ship is running in waves, there is what we call pitch motion, which is this type of motion, and there is a heave motion where the vessel goes up and down. And the wing dampens that motion. And because the motions are dampened, there is also less resistance or less drag, because pitch motions cause a lot of extra resistance.
There are no moving parts on the hull vane and therefore no maintenance.
Okay, so other than pitch and roll stabilization, there is also yaw stabilization for the yaw motions of the ship. And some examples are trim by the stern, rubber steering, and the implementation of anti-yaw skeg. So trim by the stern means that the draft is higher at the bow than at the back of the ship. So when the ship is higher at the bow, it reduces the resistance when the ship is moving through the water, and it helps to create a smoother and a more stable journey, allowing for yaw stability. For rudder steering, it controls the direction or the heading in the water, allowing for the adjustment of the ship's course, and it helps with yaw stability, since you can change the course of the ship. And for the anti-yaw skeg, it is a very special design of the ship, whereby it can help to control the flow of water around the stern of the ship, which can help to reduce turbulence and disturbances around the rudder of the ship, thus increasing yaw stability. So there are different types of yaw stability. There is the straight line stability, directional stability, and positional stability. Straight line stability means that when a ship is hit by a disturbance, it continues in a straight line in the direction that it is now facing. For directional stability, it means that when a ship is hit by a disturbance, then it changes its course of action, but it remains in the same direction as before. And for positional stability, when a ship is hit by a disturbance, it changes its course of action, but returns to the same direction and the same position it was facing before the disturbance. So these are the different types of stability, and the last stability will be unstable, which is the first one over there. So it completely changes its direction and position, very off the original path. So other than stability of the ship, we can also take a look at the maneuverability of the ship, which is the capability of moving a vehicle out of its equilibrium state to a desired state. So one example was the one that I was talking about, which was the position stability. And if you want to take a look at the relation between stability and maneuverability, they are not exactly opposites, but they are like a trade-off of each other. A stable vehicle tends to stay in equilibrium and is difficult to maneuver, while on the other hand, for maneuverability, the more maneuverable a vehicle is, the easier it departs from equilibrium, and the less likely it will return to the equilibrium state. So I've come to the end of my presentation, and thank you for your time.
So there were no comments on this. One is this one. the course stability, as he saying in this slide, the upper line is saying course stability, not ordinary stability of horizontal stability or transverse stability. This is a course stability. But for this one, if you are trying to design as a control software or autopilot, you know what is autopilot? Autopilot is very similar to unmanned car. Autopilot is popular for airplane. Okay. The human flight do not work during the main flight. They only involved in takeoff and down. During the main trip, the autopilot is working. But if you want to make a software for the control of autopilot, you need to decide which one is better for your mission. So if you want to drive in a, say, street, so you need to keep into the lane, then you need to have a positional stability. Once there is a small disturbance, you need to return back to your lane, right? But if you have, say, something like an airplane in the big space or ship is in the ocean, then you don't need to return back to your lane, right? So probably this one is better for that case. But depending on the mission, you can choose your software development directions. One more thing I want to talk is this one. You saw this device when you visit the Eureka building. We have a small experimental device there, and I guess the device you saw is this type. So there are 4 different types, right? This one is this is active control. This is passive control. No control at all. Right? This active control means pump is pushing water in some direction. But these two is only, say, semi-active or semi-passive. There is only active valve. Valve is working. Valve is trying to open the flow or stop the flow. But this one is valve in the waterway. But this one is valve on the airway. But because this is closed through, the effect is same. Right? Once the valve is closed, no air, no water is flowing. Right? But this one is not closed. But this one is closed. But anyway, once again, our system you saw in the Eureka building is this. All right. Good. Once again, and then we may move on to then discussion session.
Hello, I'm Ezekiel. I'm going to be leading the discussion session for today. So just to start us off, let's see, is anyone familiar with the 6 types of motion, the different names that they would have? Would anyone be able to tell me any of their names? It doesn't matter if you can't match it, even if you could just say a name. Sorry, 1 second. Yeah, let's see. Number 4 for roll. Oh, interesting. Okay. Yeah, that's right. Number 4 is roll. Yes, that is pitch and yaw. Yeah. Does anyone know the translational motion? Or I guess that wasn't as important.
Number 1 is search.
Yes, search.
Number 2 is sway.
So yes, sway.
And number 3 is heave.
And number 3 is heave. Yeah. Right. If talking about the translational motion, can anyone think of anything that could cause unwanted translational motion in any of the 3 heave, surge, or sway directions? And maybe why that might be an issue, why we don't want it to be moving that way.
It's mostly wave forces.
Right, mostly wave forces. In any of the 3 directions, wave forces can cause a lot of unwanted movement. X, Y, Z axis, either way. If we have unwanted motion, what do you think that might affect on the ship? Because these ships are going to be used for something, right? Would that motion affect something perhaps on the ship or the ship itself?
The stability, for example, of the payload.
Right, the stability of the payload. Yeah, especially if it's carrying a lot of dead weight, it can start to shift around on the boat, which would only further exacerbate any issues being caused by a large amount of movement. Right. Let's see. I guess it wasn't really quite covered in the slides very well, but actually, no, sorry. Can you perhaps think of something that this sort of translational motion might have on the ship itself? If it's constantly undergoing the same motions.
High stress.
Right.
Damage.
Right. Right. So, So rolling motion along that x-axis is going to be caused by similar things, right? That similar wind and wave motion. In this specific case, I suppose it would be the beam waves. Okay. Can we think of any reason why this specific axis would cause issues?
If you want to say you,
Yeah.
because this is my
Sorry.
match.
Sickness or
Right, seasickness. Yeah. I guess we can move on. I guess this is the more important part. Here I have 3 of the different methods that were proposed for stabilizing a rolling movement. Can you perhaps give me the names or how any of these methods work? Does anyone remember?
2008, but
Mhm.
for the first one,
Yeah.
when the code is going to roll,
Mhm.
it will enhance the damping,
Right.
the movement of the water.
It dampens the rolling movement by generating turbulence. Yep. I could just give you the name for that one. This one is the Bowes keel. Right, oop. There we go. Does anyone remember how the other two work?
So I don't know.
No, it's fine.
But for the second one,
Mhm.
it's very very close to the wing of an airplane. So
Right.
it will move the
Mhm.
water and flow
Mhm.
in a specific direction to
Mhm.
to uplift or
Right.
negative lifts. So that's the volume.
Yes. Thank you. All right. And for the last one.
It's I also don't remember the
It's
code.
okay, yeah, it's okay not to.
Difficult.
Hmm?
But it works by shifting the water in a way that the weight of the water counteracts the movement of the waves.
Yeah. Thank you. Oh. Now, one thing I would like to ask is, out of these three, which one do you think would be ideal? Which one do you think would work better, I suppose? Can you think of any pros or cons for any of these options?
So for the pros of
Mhm.
Insta laser, it's
Mhm.
really efficient.
Mhm.
But for the cons, it's not efficient for at low speed. I think it's more complex to implement.
Right.
Whereas beach field are more easy to put just on the hull,
Mhm.
but of course are less efficient.
Right. Shoot, I did not give myself enough space. That's it. What? Where are we? Okay, there we go. All right. Can you think of any reason why we might want or not want the anti-rolling tank?
It should be space consuming.
Right. It takes up a lot of space and weight. Oh my goodness. It's fine. Let's move it all up. I guess we can't. Oh. Sorry. All right. So once again, pitching will be caused by similar wind or waves. But can we think of any reason why pitching specifically would be dangerous or unwanted? Yep.
Passengers sickness.
Yeah, absolutely. It would absolutely make passengers feel seasick. Even more so than rolling, actually, right? Because it's even wider radius. There's a lot more movement there. Can you think of any other reason why pitching? Oh.
Well, I was thinking about
Hmm?
slamming.
Right, absolutely. Pitch slamming. Right. That can absolutely cause a lot of damage to the hull, which obviously is not ideal.
So the pitching motion, it can also happen that a lot of seawater can
Right.
get on the deck.
Right. It risks getting seawater onto the deck. Oh, that's very small. Okay. I don't know why that took so small. Can you think of anything that you could do to perhaps reduce pitching motion?
You can also use a kind of weight under the hull to stabilize the
Right.
machine. And hence, like for the fins with the generator.
Right. But now, if I may ask, would it work as well for pitching as for rolling? Because you probably want to be moving forward, right? Will that work as efficiently, do you think? No, that's fine. It's totally fine to not know. It can work just in the right configuration. I believe Diane mentioned that once. All right. And then for pitching, the main real cause of pitching is taking on waves head on, right? Is there anything we could do to perhaps minimize that happening?
If we know that there's a certain that the moves come
Mm-hmm.
the waves come from a certain direction
Mm-hmm.
because of the location of the weather or
Right.
something, we can try to make the route, change the route in a way that
Mm-hmm.
we don't go directly to the waves, but maybe
Right.
have them more from the side or from another direction.
Mm-hmm. Right. And I suppose, let's see, we can address one of these things. Is there anything that we can do to prevent seawater from getting on deck, perhaps?
I don't think you can
Mm-hmm.
avoid seawater to come
Mhm.
on deck. You can make things to make easy for water to leave the deck after, so make some hole structure, some made for
Yeah, sure.
water.
I suppose you could just say like a drainage system then. Right. Well, that is an excellent idea. I believe I believe a common response is also to raise the walls of the ship a little higher as well, especially at the front and the back. So just giving it a little bit of all right. So can you think of a situation that might cause yawing to occur in a yawing rotation?
Again,
Right.
Horse going,
Right.
but also vessel towing.
Right. But primarily vessel towing is probably going to be the more active situation. So if in vessel towing, you can think of it kind of like a chain, right? What do you think will happen if there's a slight deviation? Like, what do you think might happen there? What issue might come up?
If you are not monitoring it, you can go in direction thinking that you're in the good direction, but you are
Right.
in the wrong direction. So you will then go towards.
Once it starts turning into the wrong direction, especially if it's being towed, that force isn't going to be pulling on it straight on, right? What do you think might happen if that turning motion and that pulling motion aren't linear anymore?
It can then cause moving also in other directions.
Right, it could start turning in other directions.
In the worst case, it could also be capitalizing. Like if it comes from really hard from the force direction.
Right. Right. Do it. Can we think of anything that would specifically help against yawing?
Like for sometimes you can use swing the duration to just make it stop.
Right. I believe we could say like rudder. Right. Can I think of anything else? No. Right. Mm. Right. So now let me give you a bit more of an open-ended question. The previous ones were a bit dry. A lot of these methods do help with stability, but they also hurt maneuverability, right? It's stopping that unwanted motion, but it's also fighting against us when we want that motion to happen. Can you think of which method? Can you think which methods are perhaps better or worse to implement so that we maintain maneuverability without losing that stability?
I think it depends on also the size of the ship, for example.
Right.
For the long ballast,
Mm-hmm.
it was okay for a big ship, but not for one small ship. But maybe best methods are, for example, the one with the pin roller that you can retract when you don't want to use them. You can open it when you want to use them, so you can maintain maneuverability when you want and have a small system.
Right. Right.
This comes kind of like for any kind of active stability,
Mm.
because like with active stability, you can choose to not use it. In the case where you want that maneuverability, and then like turn it on or like actively use it the way it's intended
Right.
to have it stable again.
Is that it? Thank you. Sorry.
Question, I may say you can use a big rudder. Big rudder can help to
Turnability also coastal stability both can be obtained using a big rudder. But because we cannot use a big rudder because of the water depth, so you may use a two rudder then. All right. Good discussion, good lecture today, and then once again you have a next Thursday. No, this is Thursday. So see you next week for the ship race. All right. Thank you.